Yeah, hello and welcome. It's 4 o'clock in the afternoon. I welcome you to our third part of a series of students' online trainings. Let's show the topic of today. It's the series RFEM for students, and we have part 3, Introduction to FEM, Finite Element Method, or FEA, you might call it, Finite Element Analysis. I'm your host today and will be presenting this training. My name is Jürgen Teilmann. I've been working for Dlubal Software for nearly 1.5 years now. I'm in customer support where I deal with questions from all kind of customers. And I also give trainings, which is why I today give you this training for finite element analysis. By my side is my dear colleague, Paul Sivolgin. Paul, I can give you the time to introduce yourself, please.
Hello, I'm Paul Sivolgin. I'm a working student at Dlubal Software, and I support the product development in the area of interfaces, so the model data transfer to other software like Tekla, Rhino, Grasshopper, Rabbit, and I'm here today to answer the question in the chat for you.
Thank you. Yes, that's the point I also want to say. Today you can ask questions if there's anything you don't understand during the presentation. I will switch off my camera so you can have the full screen experience. And at first I want to show you this panel, the controls of our GoToWebinar software tool.
I think we still see the first picture.
Really?
Yeah.
Thank you for this.
Now we
It
see the
should be
panel,
better.
yes.
Great. So you have this orange arrow to show or hide the control panel. If I am too silent, you can adjust the audio settings. I just circle my mouse around this in case you don't hear me at all. Then you can click right here. Maybe the speakers are not correctly, so you can choose another one. And the important thing to keep Paul busy is to ask your questions here, but just in case you have understood anything incorrectly or say, what was he doing? Let's do this again. And also you have the opportunity to raise your hands to give a hand signal if I do anything too quickly for you today. Also, I have to say, don't worry. No one is left behind. You will get a link to download of the recording of this training, which can also be found on YouTube afterwards. And you will also get a copy of all the model files we used today, along with your certificate. Yes, let's go to the agenda of our training today. The whole series is of 6 parts. Today we are in part 3, Introduction to whatever you want to call it, FEM, FEA. So it's basically a course for our program RFEM 6. What are we going to do today? It's going to be a quite long day for us. I start with some basic principles of FEA, but don't worry, it's not too much theory. It's just to break down the walls a bit between the hard theory and your daily work as an engineer. It's kind of bridging the gap between what you learn in school and what you do as a structural engineer in your daily work. Secondary thing is an introductory example, a continuous slab, which you can also model along if you want to, if you have RFEM open right now. Is where we will model a continuous slab kind of a two-span slab to see the differences between different mesh settings and also compare it to the basic beam theory. Then I will do some other theory part about plate theory and nonlinear calculations, and also give you something to watch, some examples to further elaborate how these theories come into place when working with RFEM. The fifth is the longest part. It's handling singularities, which is a special problem due to the method of FEA. And we will show you some examples where those singularities, really nasty things, can appear and how you can deal with them. Okay, before I start with the theory part, I have something to do for you because I brought some questions and polls. So the first one I will start is just a short question. Do you work with two screens? So this is for me just to set the pace if you want to model along or just want to watch. Okay, I will close the poll in 3, 2, 1 and share the results. So the majority just wants to watch. So to you, I can say sit back, enjoy. For the other 40% who want to model along, don't worry. I will set the pace so you can model along. This shouldn't be a problem. Also, these are very easy examples, so you should be able to get along. I hide this poll and directly start with the next question, which is about your background. So have you already heard a lecture in FEA? Oh, which means did you have already heard a lecture in finite element analysis? Right, all have given the votes. This is great. The big majority knows what FEA is and what to do with it. And for the other 17%, don't worry. I give you a really short and brief overview about how FEA is used and utilized in RFEM. Good. Now let's jump back to the presentation, the basics of FEA. Computer programs are based on the displacement method. So most of you might have heard that there are two basic methods for the finite element analysis, which are the displacement methods, where the displacements are the unknowns in our system of equations, and therefore the displacements are calculated. All other results, forces, stresses, are done in post-processing. The opposite to that method is the so-called force method, where the unknowns are the forces and afterwards the displacements are determined in post-processing. But really most, if not all, computer programs utilize the displacement methods, just like RFEM does. Yeah, analytical solution for structures is hardly possible. What does this mean? You all learn in your studies a lot of methods to do analytical calculations, but if you get real structures, these are hard, really hard to be done, and you need pages of calculation. This is why the FEA method has been developed to decompose the real structure into a mesh of finite interconnected elements, which means you get a lot of small elements with a standardized stiffness parameters. Let's see where I'm in my script. And these standardized stiffness, oh, go enough. Where's my? These standardized stiffness relations can be described in many small equations, which can be solved by the computer very easily, and you get thousands of these equations where the positive side of a computer comes into place, so you get very quick solution of easy equations. In this decomposed structure, you get all the properties of the elements continuum, as you call it, at the nodes. So you decompose your structure into the mesh, and at the mesh nodes, you calculate all your results. And every result in between the nodes is done via interpolation. Mechanical behavior is done by approximation sets, which you always do when calculating mechanical properties. It's always like every other thing in physics, we use approximations that are not perfect but good enough. A very important point in FEA is the discretization. So this is how you decompose your structure into your finite elements, how you set up the mesh that resembles your structure the best to get the most accurate results as possible. So how's the procedure of an FEA calculation? You start with a structure of any kind, you just model it, and then you just break it down to a mesh of certain elements. And for all these single elements, you get your stiffness relations. Then you transform those stiffness relations to the global coordinate system and assemble these to get the global stiffness matrix of your whole structure. And that is the big system of equations which the computer solves then. And the next step, you add, it's very important, you add your boundary conditions in form of supports or maybe external forces. So the computer can solve the system. And when the equation system is solved, you calculate what I said before, you calculate the internal forces as part of the post-processing. So this was a very brief excursus, and now let's see if everyone got it correctly. I have the next question. What did I mean by discretization? Okay, 2/3 have voted. I'll give you another 3 seconds. 2, 1. I close the poll. And that's great. We have 100% of correct answers. This is really great. So I hide the results of this poll. And now we will start with our first model. Just to get this whole process done in RFEM. So I switch to my RFEM 6. This is a model we will handle later on. You don't have to model this. I start with File, New, to create a new model. And this will be our 2-span slab. So every time you create a new model, you get to the model base data. And there I start with this model name. I now call it 01. Yeah, just call it slab. You can create a project if you want to, but you don't necessarily have to. I have already created a project via this button here. I can just show you where you can create a project and give it a folder where you save all your project data. I cancel it and I go to this online training students FEM, which I created previously. And now I want to create a 2D plate model. This is the different types of model. I guess you heard before when you do some Erstab models, some member models, you can do it with 1D models. But what I want to do now is a 2D model with members and surfaces. And yeah, that's all. I want to enter here, say OK. And I start with a blank page. Just give the computer a few seconds. And now what we have here is our blank page, our new model. So I just dive in. I want to create a slab now. I have different surface variations I can create. I start with a new rectangular surface. If you don't see this button, just click on the drop down right to it and you see a rectangle and many other possibilities of creating plane surfaces. I go to rectangle and get the menu. Now we already have a thickness and a material. This is because I will just cancel this and show you again. In our data navigator, we already have sections, thicknesses, materials defined. This is just because I had these kind of objects defined in the model I have previously worked with. And now RFEM remembers those kind of objects when I create a new model and uses them again, which can be quite handy. But if you don't want them, you can do as I will do now. Right-click on materials and delete all. Yes. And now I do the same with sections. You now see I still have the sections defined, but they are now displayed in red, which means there's an error. Of course, they don't have a material assigned anymore. But I will get rid of those sections, right-click and delete all, and do the same with our thicknesses. So this is really a plain empty model now, and I start again with a rectangular surface. Now you see I have to create a thickness. I use the standard stiffness type. There are some others, but that's not what we want to address here. We just use the standard stiffness type. Then I go to the thickness where I create a new thickness using this star button. And I get to the dialog new thickness. So here I can use a uniform thickness of, let's see what I need here, 300 millimeters. So I change this to 300. And I also need to assign a material to that thickness. So we have create a new material, or again use the star button, or I can directly jump into the material library, which I do now. I clicked on the book and got to the material library, and you see a lot of materials here. So what I want to do now is to narrow them down using the filters. I use region European Union. You have many other regions, but I want to stay in Europe. And material type concrete. So this is now concrete C, C30, 37. And say OK. So now the thickness is defined, the material is defined. I say OK, and I'm still in my dialog for the surface. And I also click on OK, and now you see that I can set the corner nodes for my rectangular surface anywhere. But to do this a little bit better, to have it more in handy, I go to my view cube up to the top right corner, which I cannot use now in this mode. So I use the buttons of my predefined views, and I go into positive Z direction. So I take this top view. And now I set my corner, the first one in 0, 0, and make a slab 10 meters long and 5 meters wide. So 5, 6, 5, 10 in X direction, 5 in Y direction. I set this node, and this is my slab right now. I dismissed my current function by clicking on the right. And then I will do something to my material. Go back to the navigator on the left, the data navigator. Do a double click on the material, because I want to change something here. This is now the material from Eurocode 2. And I want to do some changes to that, because in my example here, I don't want to consider the Poisson's ratio. So I go to options on the left bottom side and hit this option, user-defined material. So now, since this is no longer material according to the standard, but a user-defined material, I can edit all these values here, and I set the Poisson's ratio to 0. Yeah, that's all for now. Say OK, material is edited. And what I want to do next is create a middle line. And this is also very straightforward. I go to my different modeling options. There we have a new single line. Click on that. And right here in the middle of my long side, so at 5 meters, I just add another line. Dismiss this option by right-clicking. And now to give you a better view, I use now the view cube to go back to the 3D. Yeah, the 3D side. And I have this line in my slab. And also I have my nodes along the line. But there is something I can show you in detail now. These are red nodes like all the others. These are standard nodes. So what I will do next, I undo this and show you something which is called, when I do a right click and go to my context menu, this function auto connect lines and members. This was deactivated right now on my computer. So I will activate it. Just check it again. You now see this function is activated. And I do the same thing again. I want to create a new line. Go again to my 5-meter point, right to the middle, across the slab, and dismiss it by a right click again. Okay, and now I have created blue nodes. And this is something special because now I have the long lines still unbroken, and these blue nodes are of the type online. So I double click on one of these blue nodes, and you can see in the main tab that there are several types of node. The red one is the standard, you can see on the right, and now it switches to the other tab. The blue node you can see on the right is of the type online, and if I switch to this tab online, you can see, okay, this node is on line number 2 at 50% of the line length. Okay, what is the advantage of this? The first thing is the long line of the slab goes through unbroken. Also, this blue node is always on the middle of this long line. So if I need to do some adjustments, you don't need to do this with me right now. I just want to show you. When I pick the short line of my slab and just use drag and drop to pull it a bit, oops. I select the whole line with the nodes. Now use drag and drop to pull it a bit out to enlarge my slab. You can see that the middle line just moved out a bit because this is bound to those lines. Okay, just to let you know. Okay. So now I will get some boundary conditions, as I said. This is now our model. So the next step is to do the supports. And this means I will use from my supports. I have nodal supports, I have line supports. I will use the line support now. The first one I get here is hinged. I have other options, and I can also create new line supports. But I use the hinged one, and I can assign it to different lines. That's what I'm gonna do now. Here, here, and here. I say OK and OK, and now you see our line supports on those short lines. They are a little bit small, so I just right click on them and use the slider to enlarge them and get the spacing between a bit bigger. So yeah, that's a view I like. That's how I leave it. Okay, so now we have the boundary conditions, and the next step is that we will enter the load. So we go a bit right in our icons, and we have the surface load. And I can enter also different types of surface loads. This is the uniform distribution in the global Z direction. And let's enter a magnitude of that load from, this is 10 kilonewtons per square meter. And assign this to our surface. I can use the pick button to pick the surface from the model, say OK, and now this is assigned to surface number 1. Say OK, and the load is created. This is also now a little bit too big for me, just my personal taste. With a right click on the load, I can use the slider to decrease its size. So this load is not just a load, this is part of a load case, which we want to calculate. And in RFEM 6, by standard, you get the load case 1 self-weight created with every new model. So I go to edit the load case. This is where I want to deactivate the self-weight. It's also something you have to consider if you create several load cases, that you don't combine any load cases which both have self-weight activated. In our case, it's pretty simple. We just deactivate the self-weight and give the load case a new name. Let's call it area load. And say, okay, and well, this could be now the slab we want to calculate. But what I want to do now is give you some comparison with different settings for the mesh, because we don't have a mesh right now. And then I will just throw a window over here to select the whole model. And then I use the function move and copy. Copy is unchecked, so I check it because I want to create a number of copies, in my case 3. So I adjust that number n to 3. I use the global x-axis for the displacement of my copies and just copy it in x direction 15 meters. So now we have millimeters in our dialog. So I'll show you how to adjust those units. You go to the bottom left, you have the question mark, which leads you to the online manual. And then this button leads you to units and decimal places. I click on it, and now you get a small red marker for every unit you have in this dialog from which you started the adjustment of units. So length is set to millimeters in my example. By default, when you install RFEM, this is set to meters, and that's exactly what I want to have here. So I set it to meters. 3 decimal places is okay. And now I can easily enter my 15 meters in X direction and don't have to worry about any calculating of other units. When I say okay, I have my 3 copies of the surface, and that's good. I hide my loads by using the button with the load arrow and the eye. So we can now go to the meshing of our 4 surfaces. At first, I go to the Calculate menu and enter the mesh settings, where you can get a target length of your global mesh settings. So this is the standard you get with RFEM, so to make a mesh size of 0.5 meter. But this is something you have to think about when you do a model. How big do the FE meshes need to be? I just neglect that, because what I do now is I go to cancel, I will set an individual mesh setting for each and every surface. So how do I do that? It's a setting for a surface, so that's something you can keep in mind for the logic of RFEM 6. I go to the types for surfaces, and there I can see my surface mesh refinements. So I do a right click and say new surface mesh refinement. And then I can set my target length for the chosen surfaces. Okay, in the first one, I want to have a really coarse mesh, 2 meters long for each element. I go to apply on the left side, we have this list. On the left bottom, I can add a new mesh refinement. I do this all in the same dialog. So now I set a mesh with a length of 1 meter. Go to apply, new one. And this now can be done really quickly. 0.5 meter, apply, new one, and this one really fine, 10 centimeters, apply. When I say OK, and just expand this section, you can see my 4 different mesh refinements, which I've created right now, but they are shown in blue. Blue means they are created but not used anywhere in the model. So I can now assign those mesh refinements to my different surfaces. So I make a double click on my first mesh refinement. It's the same dialog again. And now I can assign it using the button on the top right. So I say select the surface. For the first one, I choose the first surface on the left. And then I just go through the whole list. Refinement number 2 is for surface number 2. Refinement number 3 for surface number 3. And you can already see that for every mesh refinement, there's the surface number I have assigned it to. When I go to apply, you can see in the navigator that these mesh refinements with assigned surfaces now have turned black. So I now just assign my 4th mesh refinement to the 4th surface here and click on OK to leave the dialog. Okay, just to show you how these meshes look right now, I go again to calculate and use this generate mesh option here. And now this grid I have is in the way. I go to the really bottom line to hide the grid. And now we can compare the meshes. On the left one, you see these are highly irregular because the computer can't set a really regular 2-meter mesh into the surface. So you have a few triangles here, really weird shaped not rectangles, yeah, quadrangles, as you say, you might call them. And you see from the second mesh refinement that this looks pretty good. It's a regular mesh, and the other ones as well, but get finer and finer. Good, now I need my grid back. I activate it, and you can also go to the settings for the grid. There's a button for that. You have these dots for the grid and a hand, which means edit. And in this dialog of your work plane and grid, you can choose several options, and I go to dynamically according, I adjust the grid according to the size of the model. And I say, okay, you can now see what I mean, that the grid is only set around those existing parts of my model. Okay, so now we have, for slabs, we have them all loaded. If by any chance, when you copied those slabs to the right, you didn't take the load with, let's say now the 4th surface doesn't have a load, you can also use the drag and drop function. Just pick a load with your mouse till it turns pink. Then you can pick it with the left mouse button and drag and drop it to the next surface. You hit the control key on your keyboard just to copy it, and then this would also be repaired. So to give a good comparison of these four surfaces with our beam calculation theory is I want to create a beam for this situation right now, and that's what I do straightforward. I go to the button New Single Member, and this is really this is something I guess you have heard before. I make a beam, I choose a cross section. So since I've deleted all sections in the beginning of my model, I now create a new one. I'm already in the parametric massive sections. I choose the rectangular one and I go to the tab parametric massive, and there I can edit my dimensions. So this is 1 meter wide, so 1000 millimeters, and 30 millimeters, 300 millimeters, sorry, in height. So this is done to make it resemble our slabs with a thickness of 300 millimeters, and 1 meter just to get the loads used accordingly. I click on OK. Now our cross section is created for this new beam. The material is correctly created. I say OK, and I go to the right of my grid. I pick a point, and then I want to go into the X direction. Now I don't have a grid point for this. This is not so good, but I can, for example, choose this point with the 3 meter in Y coordinates. And if you see on the left in the window, there's a small part where I can edit the length of this member. And this is also the 10 meters. I can edit this via my keyboard and hit the enter key. Do you want to delete the mesh? Yes, of course. I want to create something new in the model. I dismiss this option with my right mouse key, and this is now 10 meters long. So if this was too fast now for you and your beam doesn't look like this, no problem. You can double click on the nodes and just enter those coordinates I have here. So X 58 meters and Y 3 meters. Okay, I also go to the right node. You just adjust this to 68 meters and 3 meters. Okay, and then your beam will look exactly like mine does here. Okay, to get those supports like I have on the slabs, I need to divide this beam. So I right click on it, say members, divide member by n intermediate nodes. So I want to divide it by one node. And I also want to use this node of the type on line, in this case on member. So I go to the options on the bottom and hit create on member nodes. So this is really dividing a member without dividing it, if you want to call it that way. I say OK, and I got my blue node created again in the middle of this beam. Okay, next I want to assign my nodal supports. Go to the section of the supports again. On the left we have assign nodal supports. And I use the hinged one, assign it to, I can do this via window, to the middle and right node of my beam. I say OK, and now I just click on apply to stay within the dialog. Because for the left node of my beam, I need another support. and create a new one where I, in addition to my Z reaction, hold the rotation around the x-axis. Say OK and choose the left node. Now I can leave this dialog using OK. Good. Next, what we need is the load on our member. There are different load types here which are easy to mix up. So at first we have a line load, which you can apply to this member, but you cannot calculate it because this load is not designed for members. This is for lines that belong to a surface. So maybe a boundary line of a surface or some integrated lines like we have with these supported lines here. So what I do now for my beam is, because it's a member, I use the member load. It's very easy to keep in mind. If you have any members, you use member loads. And now again, we have 10 kilonewtons per meter in the global Z direction assigned to member number. I can pick it now, but it's the only member I have in my model, so it's member number 1. I have the number in my head and I use it. And I will also decrease the size of this load visualization. Good, so I double click on my middle mouse button. So we have the whole model inserted in our view screen. And we are ready for calculation, but what I want to do next is to get a result section so we can get some better compare. We can compare the results better. So that's what I wanted to say. I go to the left side of my data navigator, and then I scroll down to the is it in the results? Should be in the results. Guide objects. I can find those result sections. No, not in the special objects. Result special objects. Okay, result sections are in the special objects. I must have missed it before. So I right click on it and create a new result section. So this is now, you can define any points in your model and you get a projection along maybe a local direction or a global direction. And within that projection, you cut through every surface you will find in direction of the projection, or you can pick distinguished surfaces to analyze. So I leave this to all and I set my points for the cut using this button here, pick 2 times. And I zoom in. Also, again, I hide my loads to better pick the middle point. So we have our object snaps where by standard the middle point of lines is activated. So I go to the middle of our short line on the very left, click once, then I zoom out again and zoom into the surface on the very right and click on the middle node of the short line of the very right surface. So these are now the point coordinates for our result section. I show the section direction. You can, as I said, make a projection local or global coordinates, which is now in our case the same because we have this 2D model and the local set coordinates of the surface are in the same direction as our global. And here we have, no, this is the show. I'm sorry, this is showing the section. And on the bottom right, you have the projection direction. You can use different global directions or a vector. Okay, so now this is our result section. And as I mentioned, those local axis systems for the surface, I can come to that point now. When I right click on a surface, I can switch on or off the local axis system. So you have the local set direction pointing in the same direction as of our global set direction. Now for this model, for this lab, doesn't necessarily mean that it's like this every time, but it's the case in our model. Okay, I hide this again. And I now have all set up and I want to calculate my load case. So I go to this result, show results, click on it. Computer RFEM asks me if I want to calculate this load case. I say yes. And we have, by standard, the first results we get are the global deformations. And that's something I would advise you to do every time you create a new model, to just calculate the self-weight or a simple load case where you can see if the global deformations are plausible. And this looks very plausible to me right now. I will deactivate the grid so you can see the results better. And now I get to the internal forces. I start with the member on the right. And there's a very big difference for those internal forces when you show them for members compared with the internal forces of surfaces. So I deactivate the results for my result sections. And now I just show you the internal forces of my member. So now I have my activated. It's the moment around the local y-axis of our beam. I can also right-click on the beam to local axis systems of members, toggle it on. And then you get the local axis system of the beam, which is by coincidence now again identical to our global axis system, but don't necessarily have to be. So this is now a moment bending around the local y-axis of this beam. And on the other hand, when I go to the surfaces, internal forces, I have to watch mx in this case, because on the surfaces we have the moments along this local x-axis, not around it, but along it. So it's the same with the vertical forces. You have Vx and Vy. So Vx is basically the same as when you go to the Vz of the members. Okay, so now just to clarify this, to get a good comparing of those, I switch the member results to my and the surface results to mx. And also I will again activate the results for my result sections. Okay, to better compare those values in numbers, I go to the bottom of my result navigator, where I can go to the result sections. And by standard, this is set to global extremes. So I have the global minimum and the global maximum of the whole model. But I want to compare each and every surface, so I go to the local extremes just to compare our field moments and our hogging moments for these result sections. Yeah, what we see right now on the very left, oops, it's here with this very coarse mesh. This is not a moment we would expect. This is very edgy, very coarse, and also the numbers are not what we would expect here. So we go to the right and we see the finer the mesh gets, the closer we get to the results of our beam. And there is also, this is also a very crucial point for you as upcoming engineers to get to grips with, that you don't necessarily have to make the mesh as fine as possible, because when you make such fine meshes, you take a lot of computing power. And you will see from these two surfaces here, from the left one here to the right one, there's not much difference in the results, but a lot more calculation done on the right one. So when I look at all these different results here, the first, everyone would say, I cannot use this, this is not good. But this is because I have a very too coarse mesh. And then I go towards the right and to say, okay, I want to do some economical work. I want to calculate cheap, do a fast work. My personal pick would be, from the variants we have here, would be the second to the right to use. So as a rule for you to keep in mind, to always know, is that the best way to create an FE mesh is to hold it as fine as necessary, but at the same time as coarse as possible, because these are the two opposites you need to weigh up between the precision and economical aspects of your work as an engineer. I just hide the results and also give you a little bit of a rule which you can hang on to, is that usually you have a minimum of 3, 4, 5 FE elements alongside one structural element. So this slab, the second to the left, it has these 5 elements along one slab, and this is the very minimum I would suggest you use in this situation. Go to the one on the far left. This is, you can see already that it's too coarse. You don't have to calculate, we have seen this before. So this is the main thing you need to remember from this example, to keep the mesh as coarse as possible to calculate economically, but also keep it as fine as necessary to get results which are accurate enough. Okay, I deactivate the results again, and maybe you, there was just a question I saw popping up, can't see the meshing lines. I will try to go to the display properties. Let's see if I can get them a little bit better visible for you.
So for me, they are good visible.
Okay. Okay, good. But since I'm here anyway, this is something I
maybe
also,
make a little bit darker.
yeah, I will just adjust them a bit, because that's also something I do with the grid points in the basic trainings. Sometimes I go to, which is also something really good for you to know. We have the same logic from sorting our display properties as we have in our data navigator and in our tables. So we have our basic objects, we have our special objects, we have different types. And if you run down, you have the mesh on surfaces. Go to FE elements. And now no, these are numberings. That's not what I wanted to do. This is not where I want it to be. Axis here. Here it is. The axis, and no, that's also not the one I wanted. Paul, what about you? Take a look where this can be adjusted and just give me a hint afterwards, and we will do this.
Yeah,
Just
we
to
look.
not get stuck here. But I will show you. Good. Now, maybe some of you already have taken a closer look at the results of our member on the right, because I also did a hand calculation of this exact member, where I got a hugging moment of minus 31.25 kilonewton meters, not the 0.18. Which you can see, okay, you can say it's a numerical error. It's not that much, but in our case, it has a different reason, because I will show you. Up on top, we have our static analysis settings. I click on it, and there, no, sorry, that's the wrong one. It's in the cross section. Statically analyze is something I will show you later. I go to the section, make a double click on it, and we have the option deactivates shear stiffness. I click on that option, I say OK, and calculate our load case once again. And now I get this 31.25 kilonewton meters, which I got in my hand calculation. So what is the reason for this? Is that all hand calculations are built on the so-called Bernoulli beam, which is a beam theory that doesn't consider the shear stiffness of a member. And what I now have done by deactivating the shear stiffness is turning this into a Bernoulli beam. I have a small part on this in our next theory portion, but this is just a cliffhanger to keep you awake for the next theory portion. Yeah, I will now save this model, and let's take from this model that what I have said several times now is that you use your FE mesh always as coarse as possible, but at the same time as fine as necessary to get accurate results. Okay, before we jump to the next part, I will ask Paul if there are any open questions, something I should address on the screen.
No, everything is clear.
That is good. And so now that brings me to my next question to you. I start the question. So the FE mesh size should be, please finish this sentence correctly for me. Should be really easy now for you guys. Okay, now almost a half of you have voted, now more than a half. I will give you 5 more seconds. 3, 2, 1, and I will close the question now and submit the results. So this is something I've said several times now, and most of you have remembered correctly, this that you keep the mesh as coarse as possible, just to get on the economical side of your work and to make it as fine as necessary to get accurate results. Okay, now I jump back to my PowerPoint presentation. These are again the topics I covered with our example we modeled now together. We had covered the topics FE mesh design, convergence behavior. We compared surface elements and a beam element with different mesh sizes. Also, in the result interpretation, we looked at distribution of internal forces. We looked at the shear stiffness, especially of the beam, and result smoothing. This is something we will do in depth in a later example. So the next part is plate theory, which I'm going to start with an analogy to beam elements. I already mentioned the Bernoulli beam, and the other big player is the Timoshenko beam. So what are the difference between those two? The Bernoulli beam does not consider the shear deformations of the beam. So this is what we all consider when we do hand calculation due to some table books. And the Timoshenko beam also considers the shear stiffness, which means with every shear load on the beam, you get additional deformations which are neglected in the Bernoulli beam. So next thing is the Bernoulli beam. It's characteristic that you always have these perpendicular lines to the middle axis of the beam. They always stay perpendicular to the middle line. Where at the Timoshenko beam, you get this additional shear angle, which also gives you the additional deformation you have with this beam theory. So basically, the Bernoulli beam is quite accurate when you have long and slender beams. When you have a massive chunk of a beam, you rather use the Timoshenko beam. Okay, so much for the analogy. What does this mean for our plate theory, for our surfaces? You already have heard, I guess, of the Kirchhoff theory, and there's also the Reisner-Mindlin theory, which are the big players for plates and the analogies to our Bernoulli and Timoshenko beams. So this means the Kirchhoff theory is geometrically linear with small deformations. We have a linear elastic material law according to Hooke, and we have the cross sections remain flat, not warping. We have a constant thickness, and the main thing, this is why this is bold here, no consideration of shear deformations. On the other hand, we have same thing goes for Reisner-Mindlin, except we do consider shear deformations here, and also we consider transverse and lateral strains. So what does this mean? I give you another example for transverse lateral strain, which is one thing we all know. When you have a rod and you pull on it, you don't only get your longitudinal strains on this, you also get a lateral contraction in the linear elastic part of the material defined by the Poisson ratio. Good, so and that's only taken into account in the Reisner-Mindlin plate theory. So we transfer that knowledge and get what we take from this training about those different plate theories, that the Kirchhoff does not consider shear deformations and is best suited for thin sheets of metal, maybe some sheet metal, some skins, but only with small deformations. On the other hand, the Reisner-Mindlin theory is better for thicker slabs, thick plates, maybe some concrete slab, foundation plates, something like that. And it also has a higher value approach and therefore takes more computing power. So by default, RFEM always uses the Reisner-Mindlin theory, but you can switch it, which is what I will show you now in RFEM. Before I had the wrong direction where I edited my static analysis settings, because in each and every static analysis setting, you can go to the tab Basic Settings, and there you can define your plate bending theory and, if necessary, change that to the Kirchhoff theory. Okay, I cancel that, go back to PowerPoint and get a final verdict, as you might call it, on the plate theory is the thicker the plate you want to calculate, the higher the influence of the shear, and that's where the Reisner-Mindlin theory is simply better suited. Good, now another theory part on nonlinear calculation. Yeah, just like it says here, all nonlinear calculations take longer than linear calculations, and also superposition law is no longer valid, which means you cannot simply add your load cases to get a superposition of them when you have any non-linearities in your system. Yeah, typical application areas of nonlinearities are nonlinear calculation, like second order theory analysis, you might know it better as the pi delta analysis, which is the theory for small deformations. On the other hand, if you have large deformations like in membranes or cables, you would need the third order theory. We also might need to cover nonlinear material behavior. So when we leave the linear elastic part of any material and get to the plastification, then we need a nonlinear material law, nonlinear material behavior. Also, you can have nonlinear structural elements like like members which fail under compression, or any hinges which might fail, or supports which only support in one direction, not the other. Yeah. So this is too far. Yeah. For nonlinear calculation, you have more precise analysis, but like I said in the beginning of this sheet, you increase your calculation effort and you take much more computing power. Again, it's a weighing of how precise do you need your results and how much power, how much effort will you put in your calculation. Yeah. Also, something I want to tell you about the first order or geometrical linear calculation compared to second order calculation. Many standards like Eurocode, they dictate you what theory you should use. And if Eurocode says, okay, you need to use P delta theory, then you will have to use it. It's not a question. Okay, so now I will ask Paul, is there anything unclear? Did I do anything too fast? Any open questions?
No. We just still have the question with the mesh lines, but I will answer to him. Maybe he don't have the right visibility for the model, so it's too dark in his model. But I will send him the answer.
Okay, so this is answered now. Okay, that's good. Okay, so what I will do now, thank you, Paul. What I will do now is I will show you a few models. They are just for you to watch and enjoy. You don't have to model along because these are predefined models and you will not have the time to model along with me because I just show you some results and details on them. So the first one is a frame with tension members. This is just a bit of a two-dimensional beam. And what I will show you now, I use the view cube to go to set the view against the global X direction. And I just boldly delete my bracings and want to calculate this wind load case here. So I go to calculate, and I guess you know what's coming now. We will get a calculation error. So it says some errors and warnings occurred. So in this part, I want to show you how to deal with these kind of situations. I say okay, and I get the error message, the stiffness matrix is singular. Structure is unstable. So what is happening here? We have the columns, which are of the member type beam. We have our horizontal beams, which are not really beams, they are trusses, member type truss, which you know by now have internal member hinges on both ends. So this is all hinged on top. And if the wind blows from left to right, the structure just collapses. Okay, so that's the problem what we had here. And we have now different possibilities to create bracing for that. So we can now just add a wind bracing. I just go to new single member, make it a beam using a cross section. I have my rod of 20 millimeters. That should be enough for this model. And when I say OK, I can just dismiss this right now because I still had the auto connect of lines and members activated, which is something I don't want here. So I deactivate it. And now I go back to this. Yes, I delete the mesh. And have our bracings right here. So these are just diagonal members and not connected to each other. I will calculate the load case again now. And now the structure is stable and can be calculated, but as you can see by the deformations and also by the member internal forces, when I switch on the normal forces, that we get a compression force on several of these members. We have the one, the blue one here. This is compression. Also, this is compression, but this is not something we want for wind bracing, for these cross bracings. We only want the tension. So what we can do is I select those four again using the control key. And I add a member nonlinearity. Get another tab and I can choose from different member nonlinearities. So failure if compression, that's the one I want to use right now. But if I edit that, you have a list of plenty options for member nonlinearities. So you can also have failure if compression with an amount of slippage you can define on the parameters. But I just want to use the failure if compression. Say OK. And calculate the load case again. And now I only have the tension in these members, but when I go to the deformations, there's still a bit of a bending moment. Let's compare global. So this is not exactly what I want here. I can still do it better when I edit them again. I don't use the member type beam. I can use a truss only N. So this member only. You can also see it in the bitmap on the right. This can only transfer normal forces, and using this member type with the non-linearity failure if compression, we get a member which can only transfer tension force. So I say okay and yes, calculate again. And when I deactivate the loads, then you can see this looks much more. I adjust the deformations to make them a little bit bigger. You can see that this looks more what I would expect of. And you can also see that this member here, this truss member, this is gray. The other ones are blue for the material, and this one is grayed out because this is a member that fails. So it doesn't add any stiffness to the system anymore in this load case. So another way, this seemed rather complicated. We have an easier way to do this, believe me, guys. Just do this again. To make it not so elaborate, I select those 4 beams again. I switch off the nonlinearities because we also have a member type tension, which is basically the same. You have on the bitmap, you see, okay, only normal forces of a positive magnitude can be transferred with this type of member. Yeah, okay, you see the results are now basically the same as before because it's basically the same. It's a truss, normal force only, and failure if compression. Good. So there's another example which is pretty similar to that. I will show you now, which is pretty fast to show you. If I get there quickly. So I have a very similar frame just to show you that there are some situations where you cannot solve all your problems. We already have the member type tension for this cross bracing, but we have only vertical loads in our load case here. When I say, please calculate this, and you get the same errors as before. You see stiffness matrix is singular, the structure is unstable. So what's happening here is we get the vertical forces to both sides of our frame, and basically both of our tension members are under compression. So both fail, and so the frame gets unstable again. So there is a solution for that. Again, I go to the statically analyzer settings. And this is now something the second order theory is pretty prone to. So in second order theory, you get this tab reactivation, where you have the exceptional handling of special types of member. I activate this and I get two options. So either I say failing members are to be removed individually, one by one during iterations, or I can assign a reduced stiffness to the failing members. So they don't totally fail, but they just reduce the stiffness as it says. I pick the first option to remove them one by one, say OK again, and calculate this load case once again. So this is something that can come in handy when you have a stability problem in your system with nonlinear. The nonlinearity is a difficult word. So I showed you this because it's pretty easy for me to see the problem here, because I've seen this many times. When I go back and deactivate this exceptional handling and I calculate this again, the structure would fail again. So what we can do now is edit this load case and change it to a geometrical linear analysis. I go to calculate. And then this can be done again. So now we have our global deformations done by a first order theory calculations. And you see that the bracings have failed both. So this is only stable due to linear elastic calculations. So the instability comes from the nonlinearity in the calculation. That's why we had to do this exceptional handling for the special types of members. Okay, it's 5:30 right now. I would say we make a short break of 15 minutes. So at 5:45, we will be back. Then I have a few more models for you to watch, and then we will continue with the rest of our training. Say goodbye until then and see you in 15 minutes. Okay, guys, I am back. And before we go on, I have one more thing to tease you with. Just to see if you paid attention to my last theory part. I have this question for you. Is Kirchhoff's plate theory, in this theory, is the shear deformation considered or not? So true means it is considered, and false means it is not considered. Oh my gosh, I have misread it. So it is not considered. So the statement is Kirchhoff's plate theory does not consider the shear deformation. So I think I can just skip this one. I ruined this for you. I'm sorry. I just ruined it. Just skip it. Yeah, I'm sorry for that. The question was simply that you need to know that in Kirchhoff's theory, the shear stiffness is not considered, and in the Reiser-Mindlin theory, shear stiffness is considered. Okay, okie dokes. I go back. Now, singularities is the big topic for the end of our today's training. But before we get to that, I have a few other short models I would like to show you. So the first one will be our nonlinear supports, which doesn't look like much. We have two very similar looking member models. On the left one, we have the top node with this nodal support. Where we have the node supported in both X and Z direction. And on the right-hand side, we have this blue nodal support. When I edit this by double-clicking on it, we can see that it's also supported in X and Z direction, but we have our nonlinearity failure if negative px activated. So I just show you the different possibilities for those nodal supports in terms of nonlinearities. We can, for example, it's just failure in one direction. What we have here is that when I get a force on this support in positive x direction, so in this case we have the global axis system shown, it's visible down here. So when I get a resulting force on this nodal support in positive x direction, it is supported. When I get a resulting force in the negative x direction, this support will fail. I show you this by simply calculating this load case. When I switch to wireframe, you see that there is a node load to the corner in a negative x direction. And when I calculate this load case, you now see that the linear nodal support holds the structure in place, and the nonlinear support, it fails in this direction. I go back to editing this nonlinear nodal support. So you can do all kinds of different nonlinearities. You can also make this not a stiff support, but add maybe some kind of spring stiffness to it. That's also something you can do. You have the spring visualized in the picture on the right. And you can also make it, for example, a friction support, which is something I will show you in the next model. And I'm going to the next model right now. This is number 5. This is one of my favorite basic models we have in our whole range. It's simply just a ladder, which is held in this is by the way, I guess a 3D model. Yes, this is 3D now. So we have our fully 6 degrees of freedom considered here. And this ladder is held in horizontal direction by those top supports. And on bottom, this just stands on the ground using a friction support. So I added one of these nodal supports just to show you what is done here. We have the nonlinearity friction PZ activated, and then we get in X and Y direction our parameters for the friction. And as you all know, Coulomb's the friction according to Coulomb is set by a friction coefficient. We have 0.2 edited for this. So the vertical load on this node times 0.2 gives you the maximum horizontal force that can be taken here into this support. So that's a maximum for this. So that's a maximum value for the support. And if you get over this, if you exceed this limit, the support will fail. And this is also defined for the global Y direction. Also, what we have on the different steps of our ladder is a man load. So we have a person weighs a bit less than me, so around 100 kilograms. And we have different load cases defined. So I can switch through the load cases. In every load case, the man climbs one step up. You can also right-click on the load cases and start an animation. That's something you might think is handy. Can be pretty easy to check if you have done all of these load cases correctly, just to get a quick overview. So the man climbs right to the top of that ladder. And I will. Okay, so animation has stopped. And now we want to see if he can get to the top without crashing. So I say calculate. To calculate, I have my 16 load cases, throw them to the right to say, okay, calculate all 16. And I say, okay. So now we have some errors. And I say, okay. And I just look at the global deformations. So he's now down at the bottom of the ladder. And I just switch through the load cases. He climbs up and up and up. All seem okay now in load case 12. Now we have a slightly bit of a problem. We get a maximal deformation of, this is 13 meters in total, let's say in X direction. So now you see that the friction fails and the ladder just slips away when he's on that 12th step of the ladder. So we can now make something to say, okay, he wants to step up there without the ladder failing. What we can do is I edit the load cases, and maybe now I build a load combination. Also make this the same as the load case. And I assign the load case number 12, and let's say a second man of the same weight steps on the bottom step. Now I need a design situation, just a quick. Yeah, equilibrium, that's quite okay for the thing we want to calculate here. So we have a load combination for 2 men on the ladder. And now you see the second man on the bottom gives us enough force, enough friction force to stabilize the ladder so the other man can climb up. Okie dokes, now we get to our next example, and that's a tension specimen. So what we had now were calculation nonlinearities by using a different calculation theory. We also had different nonlinearities of objects and supports. And now I want to show you a nonlinear material behavior. So what we need now is an according add-on. This is not in the basic program, but you as students, of course, get all the add-ons you need for free. So I go to our model base data, switch to the tab add-ons, and I see nonlinear material behavior is activated for this model. Okay, and now I show you this. You may know this from your lab in the university. This is a typical specimen of a tension member. And we have a line support on the left-hand side and a line load on the right-hand side. And what we will do now is we just analyze this load case. And yeah, we analyze the stresses in our model and then see, okay, now for the load is that we want to achieve a load which is just on the yield strength of our material. And to achieve that, I will add some dimensions. Just to show you, this is a surface with a width of 10 millimeters, and just switch here. So to make it look a bit better, I go to options, units and decimal places, dimensions, switch that to millimeters, no decimal places. And to make it look even a bit better, I go to the display navigator. This is really nothing you need to do right now. I just want to show you what can be done with RFEM. I need my guide objects, the dimensions, and there we can also show the units. So now we have 10 millimeters and 14 millimeters. We also need the thickness of our surface, which I can get by double-clicking on the surface, and this is 3 millimeters. So, okay, cancel. I have a steel S235, which means we have a yield strength of 235 Newton per square millimeter. Now to get to this load, this was now hand calculated by me. Down in the comment you can see how to get to this load, to get to the exactly the yield strength of the material. But if you really want to geek out on this is something I'm really excited about because I really like this. It's a computer, you can edit formulas, you can calculate this load by, let's say, okay, yield strength is 235 newtons per square millimeter. And now we can multiply this with the thickness. And this is something you have this info box. You can scroll through parameters of your model. So I say thicknesses. I have this in mind. This is something you can show later. This is thickness number 3. I will show you later. And we have uniform thickness. And it takes the 3 millimeters from this thickness 3 and also multiply it with dimensions. This also now has a numbering. The dimension I added first was the 10 millimeters. Measured length. And the second one I added measured length. And now we will also get to the 503 kilonewtons per meter that were already edited. So this is something I just want to show you. If you really want to geek out on this and want to impress someone, you can use the formula. And also, just to show you how I got to this thickness 3, I go to the thicknesses. We have thickness 3, uniform 3 millimeter. This is the one used in our surface. Now we have thickness 3. I just kept this in mind by looking at the model. So now you can get where I had this thickness 3 from. Also under the guide objects, you can look at the dimensions. So dimension 1 is our 10 millimeter width at this point where I use it for the surface, the square surface, and second for the length of our line load. Okay, just a short excursus on this. So I have added the load. We are at the yield strength of the material, and I just calculate this load case. So we have our deformations. And what I want to show you next is the stresses. So I go to surface results. The stresses, in our case, the equivalent stresses. And we use the equivalent stresses von Mises. And you will now see what's happening here is that we have a maximum stress of 268 newtons per square millimeter. And you might think that's not right. We have a yield strength of 235. We can also see where we exceed the limit by double-clicking on the color scheme in our control panel, and we can set the limits manually. This is already set to 235. so I don't need to do any changes here. Click on OK, and we have all the regions where we exceed our yield strength of the material. Also, something you may find here is that these results are not smooth. They are along the lines, the edges of the FE mesh. So this is something I want to show you under the menu Calculate, Result Smoothing. This is set to constant on mesh elements, which is the setting I recommend for doing stress analysis like this. The standard setting, however, in RFEM is continuous within surface sets, otherwise within surfaces. When I go to OK, so this looks pretty nice. You can also, when I go to the type of display, you can also make it a smooth color transition. This looks really nice if you want to have pictures for sharing on the internet or impressing someone. But for an accurate analysis, I would recommend you go to Calculate, Result Smoothing, and set it to constant on mesh elements. So, okay, but we're still exceeding the yield strength. So this is where our nonlinear material behavior comes into the game. I go back again to the data navigator, go up to the materials. And what we have now is still the material number 1. I show you by editing the surface, we have material number 1, which is S235 isotropic linear elastic. And now I have another material defined, isotropic plastic. So it's still an isotropic material, but we use the plasticity of the material. So what this means, I'm going to show you right now by editing this material. And you can see the different material models and also isotropic plastic. You get to the stress failure hypothesis. So you can use different theories here. We use the von Mises in our case, and you can edit the yield strength of the material. It's already set to 235, and we have our modulus of elasticity and the behavior in the plastic deformation. When I say OK, and we use this material model, just calculate the load case once again. And now you see that our maximum stress is the yield strength, the 235. I set this back to the maximum and minimum values, just to prove you that there's no place in the whole model where we exceed our yield strength right now. All stresses are calculated to that 235 Newton per square millimeters. I go to the global deformations once again, just to show you that we have a little bit of more deformation here than we had before with the linear elastic model. And I can also show you that we have our criteria and plastic, just to see, okay, how many of our FE mesh elements are now under plastic deformation. So that's the degree of nonlinearity currently in our model. So the next question is, if I go back to the deformations. What happens if we exceed our yield strength in our load? So this load was calculated, the 503.5 kilonewtons per meter was calculated to get exactly to the yield strength in the middle of our tension rod. But I have another load case which exceeds that limit. And if I want to calculate this now, I'll do it. And if I check our stresses, we still have, well, it's a little bit, a tiny bit over the yield strength. That's just within numerical boundaries. When we go to the global deformations, you see that you don't only get the strains along the pull axis, but you also get those lateral contractions. And yeah, this is not just from the Poisson ratio, which only applies to the linear elastic part of the material. You also get this plastification of the material, which follows the rules of constant volume, as you might know by now. Good, that's all for this model right now. Paul, do we have any questions which I should address?
No.
Good, so I have another question for you guys. And this time it's choose suitable examples for nonlinear calculation. So what of these examples is a nonlinear calculations? And please have in mind that there can be more than one correct answer. So you know now that more than one is correct, because I said more than one can be correct. Okay, I think I will close the question right now. And I submit. Okay, so well, of course, now the nasty part of this question was that all of the answers are correct. So most of you had 3 of the 4 answers picked. The third one, notes and joins. Yes, this is of course related to our nodal supports, which can be nonlinear as well. Good, so that's for the moment in our examples. And now we switch to this topic, which I really need to address, these nasty little things called singularities. Where do they occur? So singularities are points of discontinuity in a calculation model. What does this mean? They are this is not really an error of RFEM or any of our competitors. It's just a problem that comes with using numerical solutions, using FEA methods. It's just because of the discretization you buy these problems with these singularities. With other words, you get no meaningful results at certain points. Really good example I can think of is when you put your finger to the table. You can press as high as you want. You won't get any hurt till a certain point. But when you put a needle to your finger, you don't need much force to break your skin. And with a singularity, it's pretty much the same, because when you have a concentrated load, concentrated support on any point of a structure, these FE nodes are of infinitive thickness. They are almost size 0. And this means when you put any load on a point with 0 size, you get infinitive high loads and internal forces on that very point. And this is what you get basically with a singularity. A problem that comes with them is, first of all, this is not really happening in reality. This is really just a problem you get with the FEA method. Yeah, infinitive stresses and internal forces, what I said, with an infinite small needle, you get infinite high pressure. And the problem is that a mesh refinement does not improve the result. On the contrary, when you have a singularity and you refine your mesh more and more, the singularity gets bigger and bigger. So I will show you this in the next model. We have some typical singularity locations, which are, like I said, with my analogy with the needle, point and line loads, or also point and line supports. Also, when you have a surface with an opening, you can get a singularity there, especially when it's a sharp opening with corners, and you have re-entered corners, maybe a wall end. This can also lead to a singularity. Other typical locations are stiffness changes, either due to material or thicknesses, which is also something we had in our tension specimen before. You remember, this is something also needed for the real life stress, but also for our, to avoid singularities, you get some of these fillets not to have the sharp edges. Good, this is too far. I will go to RFEM just to show you what I mean with these singularities. And now I will open a new model. So guys, if you want to model along, feel free to. I will add another new model. This is again a 3D plate model. Again in my project. You don't need this, by the way. You can also create a new model without adding a project. And now I forgot the name. This is called 07 Singularities Load, for example, just to get a name. Let's see. Okay. Open a new model. And this now is basically pretty much the same like we did in our first model. I create a new rectangular surface. I need a thickness. Let's see if I have something here. Yeah, this is, no, not what I wanted. I create a new thickness, 200 millimeters, that's what I wanted. And I need a material which is not steel. I go to the library to get another concrete material, the C3037 again. This is open from before, you can also browse in the search line C30, 37. Yeah. Say okay. This is now the thickness for my surface. Again, standard. Say okay. Again, I go to the top view, and this is now from the origin of my global coordinate system, 8 meters in X direction. Whoops. And 6 meters in Y direction. Should be here. I dismiss the function. So now, and what I need is another node. So I use on the top left the function to add a new node, and I set this on. Where's my mouse cursor? It's here at 2, nope, not 2, at 4 and 3 meters. So basically the middle, right in the middle of my surface, I place this node. Okay, again, I dismiss the function. And now I want to have line supports on all 4 of these lines. So what I do now is I select the whole model. I right click on it and say lines, edit. And that's another possibility to quickly add line supports. When you're editing the line, you can say support. You get a new tab and choose, now for my example, the hinged line support. So we have this right now, right here. And we want to copy this surface again using move and copy.
Can you show the line support adding again?
Yes, of course, that's not a problem. I have now thrown a window over the whole model just to have all lines selected. And I just do a right click on the lines to edit those lines. So this is now a pretty good example for RFEM 6 where you can edit multiple lines at once. We have lines 1 to 4. This is the so-called multi-editing. And I just checked this box for support. And when I check the box support, I get another tab, support. And in this tab, I can choose again from a list of different line supports. I can also add a new one, but in my case, I want to use the first one, the hinged line support. And then I just say okay, and these supports are added. Good. Again, I throw a window to select all, and now I go to move and copy. I create 3 copies. And this is now for a displacement vector in X direction. You can also use this function to pick a vector from the model. So you can maybe choose this node and say to here, 10 meters. Yeah, I will do so. You can also enter the 10 meters here, but have in mind this is again set to millimeters. So it would be 10,000 millimeters. And I say, okay, I have now my 3 copies of the surface. And I will do the same procedure as I did before. Just to make it a bit more visible for you, I deactivate the grid. I go to the types for surfaces, like we had before with the different mesh refinements. And then I go to target FE length. This is again set to millimeters. I don't like this. I just set the units again, like I showed you before. Lengths are set to millimeters. I want it to be in meters. You can always use this red marker to see what units are changeable right now. Now I can set a target length of 2 meters and assign this to surface number 1. I create a new mesh refinement. Just go very quickly over this 1 meter. And I have in mind that this is surface number 2. So this is assigned to surface number 2. And make a new one with 0.5 meter. Assign it to surface number 3. You can directly enter it if you know the number, which I do in this model. And 1/4 meter on surface number 4. And I say OK. You don't see much at first. When I go to calculate and say generate mesh, you can see the different mesh sizes. So again, I will create a result section. This time not from the navigator. I also have a button for different result types, which are not active because I have no results now, but the result section is already active. So I choose this. And again, do the same as I did before. 2 points. I go to the very left side of the model, choose the middle of the very left outside line. Again, using the object snap to use the middle of a line. To capture this, I zoom out and zoom in to the very right side of the model. Again, using my object snap to catch the middle of that line. Yeah, this is called section number 1. Projection in global Z direction is okay. That's the setting I want to use. I zoom out and I see my result section again for this. Okay, so what we have now, we again used our surface mesh refinements. I'm going to show you once more the global mesh settings, where you also have settings for surfaces. And there, by standard, you have triangles and quadrangles. You can switch this to quadrangles only, and you can also try mapped mesh preferred. These are some settings you might need to try out and test on more complicated models. Now for our rectangular surface, there's not much to change here. So I just leave it like it is, because you see we have very regular meshes here and all built from rectangular FE mesh elements. So there's not much to change in the global mesh settings. But just in case you have some really strange looking meshes, there's one One good sentence you can keep in mind, and that's an FE mesh that looks good from a point of aesthetics is always a mesh that is also good for accuracy and your calculation. So the better the mesh looks, the better the results are. Okay, I added the load case again. We again have our self-weight load case. I added it to deactivate the self-weight because we want to have a concentrated load here, and so I rename the load case just for myself. Okay, so now I need a load. I've forgotten to do this, so I go to the section where I have my different loads and I go to the nodal load. They want a force concentrated in Z direction with a magnitude of 100 kilonewtons. So this is basically, you can see on the bitmap, a concentrated load on one node in global Z direction. I assign this to my different nodes, where I go to the first surface with that middle node. I also pick all the other middle nodes of my surfaces. And I say OK. You see in the dialog, nodes 5, 10, 15, and 20 are selected for assigning of this load. When I say OK here, I will delete my mesh, but that's OK. And I say yes. And you get the visualization of these node loads. Good. I go to calculate. And while the program runs, I'll have a drink. So, and now we have our global deformations, which look not much of a difference, but the big difference in these singularities I have created here can be seen in the surface internal forces. So I go to MX and activate my result sections. Okay. I deactivate the surface results to just show you the results in our sections. Again, I will go to the bottom of this navigator to activate the local extremes. So you have the maximum bending moment in every surface. And you see one thing that's very typical for a singularity is that the finer your mesh gets, the higher the magnitude of the internal force due to that singularity, but the smaller the area where you get that high peak. So this is very typical for singularities, that the smaller the FE mesh, the higher the magnitude and the smaller the area of the singularity. Okay, and you can also see this in the results section. So I go to this, I activate it. You can do a right click and click on result diagrams, or you can use on the top, there's a button for the result diagrams of the result section. Now we have a few results I don't want to show. They don't give much. Where are the line supports? Yeah, it's here, PZ. We don't need this. And also don't need the deformations. I just want to look at the bending moment mx here right now. You can also see on the right hand we have a very high peak, but on a narrow part of the surface. So what can you do to handle this? What can you do to handle this situation? The problem is you cannot really tell what of these results is the correct one, because neither of them are. This is really just a numerical problem. In your real life surface, you will not get such a peak when maybe a person, or well, 100 kilonewtons is a bit much for a person, or maybe a vehicle or a machine doesn't stand on one single point. So you can use a smooth range in this diagram. On top right, you have a button for activating smooth ranges. And there you can edit different smoothing ranges. So when I go to the left, this is about at a place of 4 meters. So I start a smoothing range at 3.5 until 4.5 meters with a length of 1 meters. And I want to smooth this bending moment. I add a few other of these ranges from 11.5 to 12.5 meters and 19.5 to 20.5 meters, and the third one from 27.5 to 28.5 meters. So these are my 4 smooth ranges. I want to enter here, say OK. And now you can see that we have a average of 30.69 kilonewton meters per meter. In the second surface, 31.67, then 30.69, and in the last one, 27 point something. So this is something you can use to average these peaks, to get at least a glimpse of what might be the correct solution in this case. A second possibility I want to show you how to maybe get rid of these singularities or keep the influence of them as small as possible is that I will copy this load case. I will create a new one. So I go to my active load cases and make a copy of the current one and just say OK. And in this load case 2, which is not a concentrated load, so I go back to editing it again. And I will call this free rectangular load. And in this load case, I will delete. I throw a window again over my model, this time from right to left. So I have all my nodal loads selected and I delete it. And this time I want to use in my different loads I have in hand. On the right, there's a drop-down arrow, and I can see the free rectangular load. And this is the one I want to use here right now. There's a new dialog opening, and you can see, okay, I can define different rectangles where the load is distributed. So I go to a load magnitude. This is now a surface load, so not a concentrated load of 100 kilonewton. But in my case, it's 400 kilonewtons per square meter because I want to distribute the load over a quarter of a square meter. So this means I choose the location by center and sides of a rectangle with a side A of 0.5 meters and side B of 0.5 meters. So that's a square of half by a half meter. And then I select a node. Now this first one on the first surface to get that load on and assign the load to surface. Also choose the first one. And when I say OK, you can see that this is a hovering load of these 400 kilonewtons per square meter I entered, and this is now distributed to our surface. Okay, now I will do the same. Again, the 400. Now it's basically the same I have entered before, half by a half meter. Now I pick the second node and the second surface. And now I have my second load created. And just to speed things up, I don't hit OK, I hit apply and next. Then I still have my magnitude and location of the load. Now I go to the next node. So I pick the third one. You see the second one is created. I pick the third one on the third surface. Okay. Apply and next, and I do the same on the very right one. Also the right surface. Now I can hit OK and I have my 4 loads. Okay, I calculate this again. And there you can see that is a big improvement when you just look at the peaks of these internal forces. They are now very close to each other. So you get a good impression that I caused the singularity by applying a node load to a surface. So if you now can spread the load over a surface, this is much closer to reality than the case with the nodal load I had before. Okay, I will save this model now. And if you noticed my computer is getting slow now, this is because I have many models open. So this is a high usage of my memory. And I just close all the models. So when we do our final model together, that the program should respond quicker. just close these one by one. So, okay, now we get to our final model. I open a new one. And this is really just the same we've done before. I enter a model name, this time 08. Singularity support. I again go to my project. This is also a 2D model plate. And I say, okay. Again, I create a rectangular surface. I use my thickness, which is not there anymore. Create material, C3037. Go to the top view, use the origin of my coordinate system, and this is now 8 by 4 meters. I dismiss the function, and now I will create a line support. This is again hinged, created on the right. Okay, and now I will create another node, this time at these coordinates x2 and y2 meters, just to get somewhere here in the slab. I dismiss the option. Then I will assign a nodal support. Use the hinged one and assign this to my newly created node. Say okay, okay. Now I have this nodal support. I switch back to my 3D view of it. And I will add a surface load. You know the drill. It's basically the same as we did the whole session through. Surface load. Okay, assigned to surface number 1. This looks good. This is what I wanted to have right now. Now again, the same drill. I copy all, including the load, and move and copy, create copy 3 times. Again, 10 meters. I hide my grid. I hide the loads because now, again, you know the drill. I do my mesh refinements. So types for surfaces, surface mesh refinements. Two meters on surface 1. Next one, 1 meter. surface 2, apply. You see the assignment of the mesh refinement to the surface is already written down here. We have 0.5 meter and assign it to surface 3, and 1/4 meter and assign it to surface number 4. Good. Again, I will create my result section using the object snap, middle of the left to the middle of the right, all like before. So this is now our system. I just check the load case again, just to deactivate the self-weight. This is now a surface load, and I directly calculate it. So again, we have different, but pretty similar results in deformation. But now when I look again in my internal forces of the surfaces, I go to MX. You can see again that we have a very high and narrow peak in the smallest mesh refinement. And also you can see with this type of result smoothing, which is this continuous within surface sets, that you get a very steep increase of this internal forces within one FE element. So that's also a very strong hint that we're dealing with a singularity here. So we have different options now. One thing is we have a rigid nodal support, which is something that can often be problematic. I just deactivate the results here to edit the nodal supports. So the thing is, you can edit this and maybe not make it rigid, but use a spring constant, maybe, I don't know, 10 kilonewtons per meter. You will see the effect of it. Say OK. And calculate the load case once again. You also see the visualization again of a spring. I go to the deformations. So now what we have is of course, a completely different picture of our deformation, because this nodal support by a spring, it gives us a deformation which is pretty high because I added a very soft spring. But on the other hand, the singularity is still here because it is still a nodal support. So we still have a concentrated boundary condition. So this does not really solve our problem here. So what can we do? When you make a foundation slab, you usually don't use nodal supports. You usually use a surface support just to get the load spread, to get the support forces spread over a bigger area. And what we can do now with this, maybe you have this maybe this is a ceiling resting on a column, for example. So now I will edit the nodal support because we have another option. I will edit this nodal support again. And we have, for example, our option stiffness via fixtures column. So if I say there's a column underneath this node, I activate this option and I will get another tab in my dialog, stiffness via fixtures column. And when I go to that tab, I can choose between different options. I stick to elastic surface foundations with a rectangular column head. This can also be circular. And let's say, like our free rectangular load in the previous example, I just make this 1/2 by 1/2 meter. No rotation, column height of 5 meters. You can imagine that when I shorten this column down to 3 meters, that the column itself gets a little bit more rigid, and this gives you a higher spring coefficient. You can also see and check if you want to hand calculate fixtures column like this. You can check on the bottom right the different spring coefficients that come with this type of fixtures column. Exactly. So now okay, let's do this and say okay. I will delete my mesh once again. And now you see this looks pretty different. So it has now a spring coefficient in all the 3 degrees of freedom we have for our 2D model right now. Remember that, still a 2D model with 3 degrees of freedom. And all those supports are come with a spring stiffness. So I will calculate this again now. And I zoom out. Now you will see that there's a rectangular hole in all of those 4 surfaces. So what does this mean? This means this hole represents the surface of the fixtures column we have just entered. So this is this 1/2 by 1/2 meter column. So this is cut out of the surface because the support is spread over this surface, and the internal forces on the surface are spread out a bit. Yeah, and also you can see that there are still high internal forces outside of this column. Just check the local extremes. So there is a difference in these local extremes, but you can see, like in our first model from the last 2 steps of mesh refinement, there are not much changes to the results. So you get finer, you don't get much of a change in the result, but this still is very close to our singularity. So we can do some different things now to get rid of a singularity. And the one thing is to add maybe when I use this one, I add another mesh refinement on that node. So I go to node 15, I edit that node, and I can add a mesh refinement on a node. And then can add a nodal mesh refinement. I just show this to you. You don't have to model this along with me. Make this rectangular with a side length of, well, we have a 1/2 by a 1/2 meter column. So this maybe now has a meter with a 1/10 of a meter in the inner part of it as an FE mesh length. Say OK, just to show you how this looks. So there you can refine the mesh to that very interesting point. And afterwards, you have the possibility to, when I go to special objects, you can use, for example, those surface result readjustments to smooth out those surface results. So I assign this to surface number 3. This is almost the same as we did before. We have a rectangle with 1 meter A, 1 meter B. We choose the center position. Say OK, and now we have a smoothing range that includes the whole size of our FE mesh refinement on the node. And if we just compare this, you can smooth the result, but in this case, it didn't do much good because there's always the possibility of being the smoothing range too big, having the surface refinement done too fine. So this is just an example of showing you that it can be really hard to come by a singularity. Also, if you have a peak in your internal forces away from such an interesting point, maybe a nodal support, this might not be a singularity and has to be dealt with. Okay, so that's all for this model. I just undo my last steps. This was just to show you. Okay, now to get to the finish straight, I have a final question for you, which is, where do singularities occur? Again, there can be more than one answer correct. Please answer now. Okay, I will close the question in 3, 2, 1. And I share the results with you. Well, in this case, all 4 answers are correct. The point bearings and concentrated loads were covered in my 2 examples, jumps and stiffness. were also mentioned. I also mentioned the re-entrant corners, which is also a correct answer here. The fourth one, I admit, is a little bit tricky because it wasn't explicitly mentioned, and also we have just hide this. If we look at my model here, we have a line support which doesn't bring a singularity, but if you imagine that I have a line support only to this point and the rest is just a part of the slab which is a cantilever, then you can imagine having a singularity at the end point of this line support. So I give you credit for not knowing this because this was really a tricky one. But all in all, it was a good result for this question. Good, I come to the conclusion of our today's session and training. Which is we've covered the basic topics of basic methods of finite element analysis. I've given you a few examples to see how these principles are used in RFEM. We've covered basic beam theory and plate theory, compared them. You know now the difference between the Kirchhoff and Reiser-Mindlin theory. And you also know that Reiser-Mindlin is the better theory when it comes to thick and massive slabs and plates. Also, we've talked about different mesh sizes, how you can adjust them, what you can take away from that. And we've talked of a really nasty problem when it comes to FE analysis, which are the singularities. So what I show you now, before I come to the finish, I have overstepped my time a bit. I'm sorry for that, but I don't think that's much of a problem. I will show you our website. Just switch to the English version. And there you can always look at support and learning, browse our frequently asked questions, our knowledge base. And when we come to our support and learning online training upcoming, you can look for the next online trainings we have. So here are students reinforced concrete design on the 7th of May. This is the next one. If you haven't subscribed for this, you can do so right now. And also, which I highly recommend you, on the 24th of May, Students Introduction to Timber Design. If you want to see me again, you can see me here on this day. Also, I don't know if you are already doing your final exams and bachelor or master thesis. You can always submit your thesis, which you have done with RFEM 6. So if you used RFEM 6 for your exam, for your master thesis or bachelor thesis, you can submit this, and this is not just for fun. You can have benefits from submitting your thesis. So you get posted on social media, you get a bit of a boost when it comes to starting your career as a structural engineer, and you also get a gift which comes with a 50 euro Amazon voucher, which also is something I think that's pretty good. Yes, and last but not least, if you have any questions, you can contact our support via email or down on the bottom right. This is now set to leave a message when one of our support colleagues is active in the chat. This states chat with us. And yeah, maybe you want to ask me a question, you can find me many days of the week in this chat. Good, so that's all from my side. Paul, do we have any questions left? Anything to show? Anything I have forgotten maybe?
No, I think everything is set and there are no questions not answered. So I
Great.
think everything's clear.
Thank you very much, Paul. So I would give you one last hint when I close this training session. Please stay put, stay in this session because there's an evaluation coming up. So we ask you a few questions. This will take no longer than 5 minutes. Just do the evaluation and you can give us points. So 1 point means this was a really bad training. I want to see this guy again. And 5 means, hey, Jürgen is great. I want to see him more often. Okay, that's all. I thank you very much for your attention. Have fun, have much success in your further studies, and maybe see you in 2 weeks. Thank you. Bye-bye.
Bye.